job in setting this up and coordinating it. I know it's a lot of time and effort. I appreciate that. Well, we've all seen the series Star Trek and the Starship Enterprise, that once it gets into warp drive, it can go hundreds and thousands of light years in a few minutes or so, and the crew doesn't experience any ill effects due to the accelerations to reach those speeds. Then there, of course, there's Han Solo's the Millennium Falcon, and he's able to traverse stars at ease, going again hundreds of light years in a, I guess it's a galaxy far, far away, a long time ago. Yeah. And of course, Darth Vader with hyperspace can easily hop between stars. What I want to focus on this afternoon is to take a realistic look at the basic physics of starships. Now, I looked at the official definition of starship, and there doesn't apparently, one doesn't apparently exist. But this seems to be a definition generally accepted by NASA and other activities working on deep space probes. So a starship is a deep space probe which will leave our solar system and wander the interstellar medium. There are some starships that have been launched by NASA, the Jet Propulsion Lab. Voyagers, New Horizons, and Pioneer 10 and 11. I'm going to focus on the Pioneer 10 because it was the first probe to escape our solar system, and it was launched in 1972. It's launched on an Atlas Centaur rocket from Cape Canaveral. The weight's about 571 pounds. It could generate 155 watts of power. The mission duration is 30 years. The principal objective wasn't to go outside our solar system, but the principal mission was to photograph Jupiter. But based on its trajectory, it did photograph Jupiter and reached the limits of our solar system in 1983. It had a 30-year life, so the batteries and equipment wore down. The last signal NASA received was in 2003. In 2012, NASA figured its velocity is 26,930 miles an hour relative to the Sun. And the distance from the Earth is about 10 billion miles. If it keeps going on its current trajectory, it's pointed towards the star Aldebaran, and it'll reach there in 2 million years. Because Aldebaran's only about 4 times 10 to the 14 miles away. Now here's an artist's concept of Aldebaran. It's a supergiant. And here's a picture of our sun. It's sort of small in comparison. Okay, Pioneer 10 does carry a plaque. It's gold anodized aluminum. And it's there in case any intelligent life forms intercepts it. It has nude figures of a human and a female. It's got a description of our solar system depicting the location of Earth and a pictorial of Earth sending messages to it. And this plaque is attached to the antenna support struts to protect it from interstellar dust. There was a movie put out based on Pioneer 10. It's called Starman, and oh, you saw it? It presumes that an intelligent life form intercepted Pioneer 10 and came to pay us a visit, and as soon as it entered our atmosphere, we shot it down. So. Okay, I'd like to talk a little bit about alien planets this afternoon. Alien planets are also called extrasolar planets. They are planets that are outside our solar system. It's a fairly recent discovery. The first one was discovered in 1992 by two astronomers, Alexander Wolskan and Dale Frail, and they were working at an observatory in Puerto Rico. Most of the extrasolar planets have been found using the Doppler effect. When astronomers sees a blue shift or a light shift, a blue or a red shift from the light from the star, they got to conclude that something is causing this, and they rightly assumed it's caused by the planet's gravity tugging on the star. So then they can use Newton's laws and Kepler's laws to obtain some characteristics of the planet. So Doppler's an interesting effect. It occurs when a source of light or sound is moving with respect to an observer. So if the source is moving towards an observer, a higher frequency and a shorter wavelength is experienced. And when it's moving away from the observer, just the opposite effect. And here's a pictorial of it. Suppose we have an ambulance with its siren going. If it's moving towards an observer, that observer is going to perceive a higher frequency. If it's moving away from the observer, that observer will perceive a lower frequency. And here's the equations for it. It'll be the frequency that you observe. F is the frequency it should be, and v is the velocity of light. Now we know we've observed this parameter, we know what the frequency should be, we know what the velocity of light is, so we can compute the velocity of the source. We know what radiation should be coming from the stars, we know what elements they are, we know what the frequency of the light and radiation should be. So if we're measuring a frequency different than what it should be, we conclude that there's got to be a planet in the vicinity of the star, and it's making the star move either towards us or away from us. And here's just a pictorial of the electromagnetic spectrum. Goes from radio waves to X-rays and gamma rays. Visible light is in a small portion of the spectrum here. Okay, most of the planets that have been discovered are huge balls of gas. And they're very close to the star. They're even closer than Mercury. So the planet's going to be many times hotter than what we're experiencing on the Earth. And here's an example of the planets that are discovered orbiting stars. They're very similar to Jupiter, which is a huge ball of gas. So that's not saying that there are not planets similar to the Earth orbiting these stars. What it's saying is we don't have instruments enough, or instruments that are good enough or sensitive enough to perceive the small Doppler shift that a small planet would generate by perturbing the star. So as our technology advances and we're able to develop devices that can perceive smaller and smaller Dopplers, we should be able to find planets similar to the Earth. If that does happen, it would be neat to send a Starship out there to investigate any possible life forms, or if that planet is suitable for colonization. Okay, before we start building this Starship, we better look at some of the issues involved. The first is the speed of light. It's 3 times 10 to the 8 meters per second, or 671,000 miles an hour. Now this isn't like 60 or 70 miles an hour that we experience with our cars. It's 671 million miles an hour, or 186,411 miles per second. And just to compare the speed of light with some of our more rapid vehicles that we're familiar with, the space station is 18,000 miles an hour. Meteors, we can generally clock at over 20,000 miles an hour. And of course, the speed of sound in dry air is 745 miles an hour. So jet planes can routinely exceed the speed of sound, maybe going to twice, sometimes 3 times it. But as you can see, we're orders of magnitude away from even approaching what the speed of light is. Okay, I'm going to focus on Alpha Centauri only because it's the nearest star to the Earth and maybe something we can reach in the near future. It's a star similar to the Earth. It's about 4.3 light years away. Its mass is pretty close to the Sun, and its radius is comparable to that of the Sun. Okay, when we start thinking about starships, we got to address the issue of a light year. And a light year is the distance that light travels in 1 year. So if we look at the speed of light at 671 million miles an hour, there are 8,760 hours in a year. So if we multiply the speed of light by the number of hours in the year, we come up with 5.88 times 10 to the 12th miles. So the distance to Alpha Centauri is 4.3 times a light year. So if we multiply 4.3 times the distance light travels in a year, we come up with a figure of 2.53 times 10 to the 13 miles. And I don't know what this is. It's way past trillion. I don't know, maybe a gazillion, something like that. But just to compare, here's the distance to Alpha Centauri. The distance from the Earth to the Sun is 93 million miles. From Jupiter to the Sun is 483 million. And the distance from Pluto to the Sun is 3 billion miles. But that's still so significantly less than the distance to Alpha Centauri. So it's far, far away. Okay, in summary, the distance to Alpha Centauri then is about 1 million times the distance of the Earth to the Sun. Okay, when we're designing spacecraft, we have to, or airplanes, we have to take into account acceleration. It's an important parameter. And so generally, spacecraft and aircraft designers refer to a concept called G's, where 1 G is the acceleration near the surface of the Earth, and that's 9.81 meters per second squared. Of course, we're all experiencing that acceleration, so that's not a problem. If we bump that up to 3 Gs, that's generally the acceleration of fighter pilot experiences in a high-speed turn. It doesn't cause too much of an effect on the fighter pilot, but he can't do that forever. If you get up to 8 Gs, this is pretty close to the limit that an astronaut or fighter pilot can withstand. If you get up to 10 Gs, we're talking about accelerations that are going to start killing humans. If we're, again, designing spacecraft, we have to look at the components in the spacecraft, and the component in the spacecraft that's most susceptible to acceleration is electronics. And a conservative estimate of what electronics could withstand is about 1,000 Gs. I mean, this again is conservative. Well, let's take a look at the length of time to reach different velocities at different accelerations. If we're going at 1 G and we want to reach the velocity of the space station, 18,000 miles an hour, we can do that in about 13.7 minutes, so that's not an issue. And of course, for electronics, we can reach this velocity in less than a second. So getting up to the velocity of the space station isn't a major problem. And we're talking about going to the star, traveling at the speed of light. At 1 G, it would take 5.06 weeks to get up to the speed, a tenth of the speed of light. And for electronics, it would be less than a minute. So again, it's a lengthy interval, but it's certainly not excessive. It's certainly doable with our technology. Okay, if we want to get up to the speed of light, if we go at 1 G, it's slightly less than a year to reach the speed of light, and about 8.5 hours at 1,000 Gs. But still, these are not excessive numbers, so this is really not a showstopper in Starship design. But I think we could, or not easily, but we could handle the accelerations involved. The hooker here is Mr. Einstein and his theory of relativity. We have to address the issue of relativistic mass. And the equation for relativistic mass is m relativistic equals rest mass divided by the square root of 1 minus v squared over c squared, where v is the velocity of the starship with respect to the Earth. And so m would be the mass of the starship on the Earth, but m relative is the mass of the starship relative to the Earth, or as perceived by the Earth. Now, for the sake of calculation, I'm assuming that the mass of the starship is 212,000 pounds, which is the mass of the Saturn V in orbit. This is a typical mass of rather large spacecraft. And I've computed, or I have a listing here, or a list of velocity of this starship or spacecraft relative to the Earth, the mass of the starship on the Earth, and the relative mass of the starship as perceived by the Earth. So if we're going at the speed of the space station, about 20,000 miles an hour, we don't see any increase in mass. If we get up to a tenth of the speed of light, we see a slight increase in mass, about 1,000 pounds increase from the rest mass. If we get to 9/10 the speed of light, we see that the mass doubles from the rest mass, or over doubles. But here's the real clicker. When we get to the speed of light, the mass becomes infinite. So this is telling us we cannot travel at the speed of light. What happens is the energy that we put into the starship to make it go faster is converted into mass. It's the exact opposite of an atomic bomb where mass is converted totally into energy. So So according to Dr. Einstein, we are not going to be able to travel at the speed of light. Now there is some work going on trying to get around this. And I guess there were some concepts in the Interstellar movie, black holes and wormholes, but that's still a little far out. Okay, let's talk about times to reach Alpha Centauri. And we computed the distance to Alpha Centauri before as 2.53 times 10 to the 13 miles. If we focus on going at a tenth of the speed of light, we know that the velocity of the starship is equal to the distance to Alpha Centauri divided by the time it takes to get to Alpha Centauri. And of course, just by doing a little bit of algebra, we find that the time to Alpha Centauri is the distance divided by the velocity of the starship. So that comes out to be 3.77 times 10 to the 5th hours. And if we multiply that by the number of hours in a year, we find it takes 43 years to get to Alpha Centauri, traveling at a tenth of the speed of light. Now if we go to 9/10 the speed of light, we can do that in 4.78 years. But then the mass of the starship will double, and so we're going to need more fuel and everything else. Quite a bit more fuel. Okay, another factor that we have to consider is time dilation. And this again comes from Einstein's special theory of relativity. Time dilation, delta T, is the time on the Earth. Delta T0 is the time on the starship, and that's all and the relationship is delta T equals delta T0 divided by the square root of 1 minus v squared over c squared. Now, for those of you who saw the movie Interstellar, you remember that the astronaut went to a distant star and he had a much younger daughter. And he comes back from his visit to the star, and he's only aged a year or two, where his daughter was an extremely old lady on the point of death. And the reason for that is time dilation. Okay, well, just to put it in perspective, if we're going at a tenth of the speed of light, the time to reach Alpha Centauri from the Earth's perspective would be 43 years, but if you're on the starship, it would be 42.8 years. If we go, so you save a little bit. Time dilation is working in the favor of the starship designer. If you're going at 9/10 the speed of light, the time to reach Alpha Centauri would be 4.7 years. Earth time, but on the starship itself it would be less than that, 2.08 years. So time dilation is working in the starship designer's favor here. Okay, next I want to talk about some of the concepts that are in the open literature for traveling at these higher velocities. And I'm going to call them relativistic velocity. That's a term normally used by physicists. And a relativistic velocity is velocity comparable to the speed of light, such as a tenth of the speed of light, 9/10 the speed of light. The first project I want to look at is called Project Daedalus, and it's a nuclear pulse rocket. It's probably the most comprehensive design of all the concepts. It's a design put forward by the British Interplanetary Society, and they worked with the British aerospace industry to, they took a good look at it. It's just a paper study, nothing's been built, but it's kind of scary concept, I think. It actually employs nuclear bombs detonated beneath the vehicle, and the vehicle is fitted with large shock absorbers, which absorbs the energy from the nuclear explosion of the nuclear bomb and transfers the energy and momentum to the payload. Now, Project Annandale focused on an interstellar journey to Barnard star, which is about 6 light years away. And so it figured that the journey would take 50 years, and the maximum velocity that the Dallas could obtain is about 12% the speed of light. The reason I was focusing on a tenth of the speed of light is that's where the concepts for relativistic velocities are. Okay, the total mass of Dallas would be about 106 million pounds. And that would only get the rocket to Barnard star. If you wanted to decelerate, you would probably have to double the size of the rocket. And here's an artist's concept of it. It's quite a large design, and it's comparable in size to the Empire State Building. We're not talking about anything trivial here when we talk about when we take a realistic look at starships. The other concept that's out there is called an ion thruster. And this uses electrostatic or electromagnetic forces to accelerate a reaction mass. And the reaction mass is a stream of ions. Now an ion is, let's take an atom, and let's strip off all its electrons so it will have a positive charge. And so an ion would basically be an element or a molecule that lost its electrons. So an ion thruster first has to strip off the electrons or ionize the atom, and then it has to create a voltage gradient to accelerate the ions to a high velocity. And of course these ions are going to be the exhaust mechanism for the rocket. The reason for going with ions is that they have a large velocity after they've been accelerated. And that's important for rocket design. Here's a basic equation for a sample rocket. And we see v is the velocity of the rocket, v0 its initial velocity, u is the velocity of the exhaust gas. We have the initial mass of the rocket and the final mass. The point I want to make here is that the greater the exhaust velocity, the greater the speed of the rocket. So that's what's driving scientists to think about the ion for thrusting, because these ions can reach relativistic velocities, and they can make the rocket go far faster than ordinary propellants. And to accelerate an ion, again we have a charged particle. We have a capacitor. We have a voltage applied across the capacitor. And let's say this is the positive terminal of the capacitor and this is the negative terminal. And if we punch in a small hole here, the ion comes in, and let's say the ion is negatively charged, it will bypass this negative plate, won't experience it, but it'll be attracted to the positive plate, and so it will gain velocity, and then it will accelerate through the hole in the bottom portion of the capacitor. The force that the ion experiences is just Q times the electric field, and from that we can compute the acceleration and the velocity that the ion obtains in passing through the capacitor. Here's an artist's concept of it. We have the power processing unit, the supply to propellants. The propellant goes into the ionization chamber where the electrons are stripped off. It passes through a capacitor here where it gains energy. Then it goes outside of the rocket, providing the thrust. And of course, the thrust is provided by Newton's third law. The rocket exerts a force on the ions that are going out, but the ions exert an equal and opposite force on the rocket, which propels it forward.
The neutralizer, I've seen these diagrams before, but I haven't paid attention to the neutralizer. Is that so that we're not leaving an ion trail, or is that just the leftovers of the stripping the electrons? We need to do something with that. I don't think it's important to mask our ion trail unless we're being chased by aliens.
Yeah, you want to get rid of the neutral ions in here. You don't want to expel those because they're not going to do anything for you. So if they're not ionized and they're not accelerated, we're going to expel them.
Oh, so the neutralizer is just removing neutral ions that have not been ionized. Oh, cool.
Okay, the next concept is a solar cell. Oh, and the ion thruster, that can generate speeds on the order of a tenth of the speed of light. So, like I said, most of these concepts are around that. The solar cell is a highly reflective spacecraft that uses gigantic supercells. And it uses photons of all elements, photons that come from the sun to propel it. Now, the thrust from a solar cell is very low, but it's inexhaustible. It goes on forever, not like with a rocket that can only provide a thrust while it has fuel. And the solar cell is constantly thrusting in a direction of motion. So a Starship employing solar cells, again, could reach Alpha Centauri in about 50 years. So we're talking about fairly close to a tenth of the speed of light again. And here's NASA's been looking at solar cells, and here's a pictorial of what they feel one would look like. Okay, the next concept I want to go over is the space-based cyclotron, and it's a concept that I'm evolving. So I'm going to spend a few more view graphs on it. Maybe it's a little parochial, but what the heck. It employs the same principles as the first cyclotron that was put into operation by Lawrence in 1932. And again, the cyclotron accelerated elementary charged particles by passing the charge through a capacitor a large number of times. And here's a sketch of the first cyclotron. There would be a magnetic field that's perpendicular to the page. And we would have an ion source, and an ion would go into this magnetic field, and it would have an initial velocity, so it would start going into a circular path. These D's here are basically capacitor. When it reaches one phase of the capacitor, it goes through it and it's accelerated and it spins around, and when it reaches this point here, the polarization on the capacitor changes, so the polarization changes again and it's accelerated at this point. Continues doing that a large number of times until it reaches the limit of the cyclotron, and there's a deflection plate here that sends the ion stream off into whatever experiment the researcher wants to perform. Okay, the space-based cyclotron again uses the same concept. the charges are placed on probes, and they're accelerated to high energies so they can achieve relativistic velocities by passing these charges through a capacitor a large number of times. Now there's a basic assumption made on with this concept, and that's that 16 coulombs of charge can be contained in 1 cubic meter of volume. And that's an awful lot of charge. But I was in contact with Los Alamos National Laboratories in the 1990s, and they were working on non-neutral plasmas. And they gave me a projection that they thought that it would be a tough task, but they thought that eventually it would be possible to confine 16 coulombs of charge into 1 cubic meter of volume with a non-neutral plasma. So based on this assumption, I continued on with the concept. Okay, so again, charges are going wrong. Okay, here's the basic concept. We have a spacecraft with a charge on it, and we have 2 probes with charges on them. One of the probes has a capacitor on it. Now these probes rotate about the spacecraft, and what keeps them in orbit is the electrostatic forces, or Coulomb's law. Again, it's similar to the force of gravity, but these are electrostatic, or electromagnetic forces. And here's Coulomb's law, and this is the force that keeps the probes in orbit about the spacecraft. Again, it's a 1 over d squared or 1 over r squared force, similar to the force of gravity. Now, rockets will first place the probe M1 and M3 in an orbit around spacecraft M2. After each encounter, probe M1 and M3 will increase their velocity, and the radius of the orbit will increase by the same amount. And then half an orbit later, there'll be another acceleration process. And this will continue until the desired velocity is attained. At the end of the acceleration process, the charge on spacecraft M2 will be dropped to 0 together with the voltage across the capacitor on probe M3. And the 2 probes will go off in tangential trajectories. Now the 2 probes will be the Starships, and the spacecraft will remain in Earth orbit. And the probes will be vectored to the star of interest with rockets. The rockets will just be used for steering here, not for acceleration. And this is kind of what I had in mind. Spacecraft M2 will consist of 2 satellites, or 2 spacecraft. There'll be the orbital charges on spacecraft M2, and they'll be keeping probe M1 in orbit. These are the orbital charges on probe M1. Probe M1 will also have what I call an accelerating charge, and the second part of spacecraft M2 will keep probe M3 in orbit, and M3 will have the capacitor, which will provide the velocity and acceleration to probe M1 as the accelerating charge passes through it. One intriguing feature about this concept is once you reach the star of interest, you don't have to carry extra fuel on board to decelerate it. there should be a magnetic field around the star of interest. There is one around the sun. Upon entering the magnetic field, charge Q1 and charge Q3 will be activated. The polarity of the capacitor will be changed, so instead of an accelerating potential, we'll get a decelerating potential. And the process will continue until you decelerate down to the desired velocity. And I guess I said all this. A number of designs are possible with this concept. I just looked at one where the probes would be, program 1 and program 3 would be about 1,650 pounds. I had the rockets accelerate the probes to about 1.4 times 10 to the 4th meters per second to start the acceleration process. And I took it to a tenth of the speed of light. And with this concept, it would take about 62.9 days to achieve the velocity of 3 times 10 to the 7 meters per second, or a tenth of the speed of light. And so the probes could reach, excuse me, Alpha Centauri in 43 years. Okay, manned space flight is, or manned starship flight is another tricky concept here. I guess if you listen to the movies, there's the effect of hibernation, where they put the astronaut to sleep for, I don't know, hundreds of years, and they wake him up after 100 years, and he hasn't aged at all. I don't know, that may be possible. But I think the space arc is maybe a little more doable. It was first proposed by a Russian teacher named Tylowsky over 100 years ago. In 1929, another physicist, Burnell, kind of advocated this concept in his book on interstellar colonization. In 1973, Arthur Clarke, who was the chairman of the British Interplanetary Society, did some preliminary calculations on this concept. And this his design appeared in a book, a fictional book he wrote called Rendezvous with Rama. And so why is space art? Okay, the current concepts for reaching relativistic velocities are around 10th of the speed of light. If we're going to go to Alpha Centauri with this speed, it's going to be like 43 years. If we go to 9/10 the speed of light, which I haven't seen any designs yet, but that would take 4.78 years. The whole point is, if we're going to do any kind of star exploration with starships, we're going to be up there a long, long time. So the space arc proposes a gigantic cylinder, and the crew would live on the inside walls of the cylinder. Okay, here's a pictorial of it. So we have a giant cylinder, and it's going to be rotating such that the inside, on the walls inside the cylinder, we will simulate 1g of gravity. So we'll have the same gravitational force on the inside of the cylinder as we experience on the Earth. Now, spaceships that are journeying or flying to the space arc will land at a central point called the hub. There will be 3 stairs leading down to the inside of the cylinder. At the hub, the acceleration due to gravity will be 0. So it'll be weightless at the hub. But as you start coming down the steps, the gravity will increase until when you reach the inside of the cylinder, it'll be 1G. Now the Ark is really going to be a self-contained system. It's going to have a river going around the central portion of the Ark. The crew living quarters will be located here. There's also going to be animals on board because it's a long, long journey. There's going to be farmland. There's going to be propulsion. I think it would be really weird though if you're sitting on a boat on the river, and you look up and the river goes like this, all the way up, all the way behind you. Okay, the concepts that have been out there talk about a length of about 31 miles. The diameter of the ends are about 12.3 miles. The thickness of the shell is 1649 feet. The width of the central river is 6 miles, and the rotation rate is about 621 miles an hour. That'll give you about 1G of gravity inside the walls. The mass is on the order of 1.31 times 10 to the 7 pounds. This is roughly the size of an aircraft carrier. The illumination would be 6 arrays of light running along the length of the cylinder, and they would be powered by some type of nuclear fission or fusion if it ever becomes practical in the future. And all food, air, and everything else has to be recycled. It's going to be a self-contained unit that's up there for an awfully long time. Okay, in summary, hyperspace and warp drives are really in the distant future. We got a long way to go. The current Starships that are out there are Voyagers, New Horizons, and Pioneer 10 and 11. It's a long way to the stars. Our nearest neighbor, Alpha Centauri, is about 1 million. The distance is 1 million times the distance of the Earth to the Sun. The time to reach Alpha Centauri would be 43 years, and the reason, and that's at the speed of 1/10 of the speed of light, which is where the current proposals are to retain relativistic velocities. Einstein, with his theory of relativity, will not allow traveling even at the speed of light. And there, like I said, are a number of proposals to go to 1/10 of the speed of light. If we're ever going to do something like this, we need a commitment. In 1883, the Russian teacher first proposed that rockets could operate in the vacuum of space. Rockets at that time were little more than exotic firecrackers, but we did have a firm commitment to get to the moon, and in less than 100 years we landed people on the moon. So we really need a commitment to go to the stars. And again, it's a fascinating universe out there. We need to figure out ways to get out there and explore it. That concludes the seminar. Are there any questions? Yes.
Did the satellite to Pluto, was that ion charged?
That was just the distance to Pluto. You
the
mean
spaceship that went to
Pioneer
Pluto?
10? No.
I thought there was a special propulsion for that satellite.
That I know of.
I think it's regular.
No, they just shut it out there and let gravity take care of it.
They were
Yeah, no, there
impatient,
was
they
a
could have used
flyby by
ours.
Jupiter that put it out there, but it was regular.
I thought there was a special propulsion for that one. Anyway.
They went straight into the solar escape orbit, which hadn't been done before. It might be what you mean. They didn't have any parking orbits on Earth.
You got there pretty quick in 10 years.
Yeah.
Yeah, it did. With gravity assist. Okay, well, thanks for coming. Oh, another
The
question.
river, why is it flowing? Shouldn't it just be a lake? Like, why would it flow? Is there a
That was the concept that Clark put together. So. I guess you could just have a lake that would.
There should be some a level of viscosity in the river. Can we assume that
I
the
was thinking
it's still
maybe
alive?
swimming would cause it to float.
What's that?
Sitting, yeah. The pipes the way
I
it's
think
Canadian, you go in
The book was published, I think, in the late sixties, so I'm not sure it's still alive or not.
As it's 72.
I'm sorry?
In 1970.
72. All right, well, thank you all for coming. I hope, well, there was, got something out of it.